All right, here we go. Chapter 10, Alkanes. So let's dig into this a little bit. We'll go through a little bit of this introduction. This is the start of the semester, so I got to remember how I navigate through here. There's got to be a better way of doing it than this. Okay, organic. You going to HEB? Organic. Kind of. What's organic? It's actually natural. It doesn't have a lot of synthetic chemicals on it. Pesticides, herbicides. So organic is kind of relating to living, natural, that sort of thing. Organic chemistry, which is carbon-based chemistry, back in 1800s, it was believed that only living things could make those kinds of molecules. So when the very first simple organic molecule was made in the laboratory and someone wrote a report on it, wrote a paper and submitted it, everybody laughed at him and said, it had to be a scam, because only living things could make those kinds of molecules. It was very simple. Urea it's a naturally occurring molecule that our bodies even produce, and we eliminate it. But someone made urea and said, I made this in the laboratory. And everybody thought, he's lying. And then they tried it, and other people were able to make that molecule in the laboratory. And on came organic chemistry, organic chemicals, carbon-based. So just the way we go in and buy organic foods today and think that's kind of a little bit more natural and from the biological system, that's what they thought then too. So the study of carbon compounds. Life depends on organic chemistry. Biochemistry is the field that studies chemicals of life, and what we're going to see is that all the biochemical molecules are carbon-based. Sugars, carbohydrates, fats, proteins, DNA, RNA, they all have a very fundamental carbon backbone or nature to them. These just get a little bit more complicated. But when you think of an organic chemist today, you're generally thinking of someone who is synthesizing a carbon-based molecule that may not be found in nature. Aspirin's a good example of that. They start out with salicylic acid, which you can get from willow trees. And a lot of drugs actually have their origin in something that is produced in nature for thousands of years. My head hurts, Mom. Okay, go chew on a willow branch. And the headache went away. And they knew this. The cultures knew this. What did it? Who knows what did it? But chew on the willow branch and you'll feel better. Well, that's salicylic acid. And aspirin is acetyl salicylic acid. So you don't find aspirin in nature, but the starting material, salicylic acid, is something that natural organisms produce, like the willow. All right, organic chemistry, foods, as we mentioned here, carbohydrates, fats, proteins, clothing, silk, linen, wool, cotton. These are all naturally occurring fibers, carbon-based fibers. Dacron, nylon, Orlon are synthetic fibers. And Kevlar. Kevlar is what goes into bulletproof vests. It's a fiber. It's extremely high tensile strength fiber that, woven enough of those together that can actually stop a bullet. So Then plastics. All right, let's answer one question that's on the first quiz. Look at that nice, clear, colorless plastic bottle. Okay, we'll see what that is in chapter 11, I think. Polyethylene terephthalate, that's that plastic. Where's that come from? What's the starting material to make that plastic? Polymer. What? Polymer. Well, it is a polymer, but that's not the starting material. What? Like oil. Oil. All right? So all these plastics are made from crude oil. You take crude oil, heat it up, or add some chemicals to it to crack it or break it down into ethylene. Ethylene we'll see in chapter 11. And then you make polyethylene, which is Ziploc baggies, or that'd be low-density polyethylene, or you make high-density polyethylene, which is like a milk carton. The plastic, since in milk carton, you can make polypropylene, polystyrene. This is polyethylene terephthalate, so it's actually making a polymer. You're right, but we don't get it from polymers. It is a polymer. And what we're doing is polymerizing monomers that we get out of crude oil. So we're not just burning it in our cars or putting what's left over on our highways as asphalt. We are cracking out, distilling out different monomers and then making certain things out of them, certain plastics. So you can get this nice, beautiful, clear, pure polyethylene terephthalate from that nice, black, ugly petroleum. So plastics, multi-trillion-dollar industry. Pharmaceuticals, detergents, soaps, pesticides, gasoline and oils, water purification, goes on and on and on, what we're doing with chemistry. Okay, now these are this comes in at the beginning of chapter 10, and we won't dwell on this. We could spend all day just describing these different kinds of bonds that you find in certain chemicals, organic chemicals. And they define the class of organic compound they would fit in. And we call this is the group there, or the functional group. Why? Well, this carbon-carbon double bond will function differently in chemical reactions than a carbon-carbon single bond. This carbon-carbon triple bond has additional functionality. An OH group on a carbon is what makes it an alcohol. So the functional group is that OH or hydroxyl group. Alcohols will react differently than alkanes or alkenes. There's your ether. This R is just a general, it's just saying any kind of carbon complex over here bound to another carbon complex over here. So really, here's a simple ether. This is dimethyl ether. Dimethyl ether. So what is an ether? A carbon-oxygen-carbon bond is the functional group in ethers. All right, so like I said, here's what this is going to be. This is going to be chapter 10. This is going to be chapter 11. This is chapter 12. All right, so your exam is going to be over those. So don't get bogged down in trying to learn what alkenes and alkynes and alcohols are right now. We'll do that next week. We will do that. But like I said, digest a little bit at a time. Okay, over here we have aldehydes. Now, what we're starting to see here is this kind of a bond. A carbon-oxygen double bond makes an aldehyde. And, for example, this might be an R. What's an R? An R could be another carbon. It could be 2 carbons, 3 carbons, 7 carbons, 12 carbons. It's just a general letter to say there's any kind of organic group attached to that is an aldehyde. And then this is a ketone. You got a carbon-oxygen double bond, but it's between 2 carbons. The aldehyde, the carbon-oxygen double bond, is on the end. This is chapter 13. Then you get the carboxylic acids and esters. That's chapter 14. So what this is trying to show right here is something that looks like this. So this has a carbon-oxygen double bond and a hydroxyl. This doesn't make it an alcohol. This is not an alcohol. It's a carboxylic acid. And if you put a methyl group on there, you have something that you not only are very familiar with, but you have tasted before. This is acetic acid, which is in vinegar. It's a carboxylic acid. Okay, so now you saw the hydroxyl, that makes an alcohol. Carbon-oxygen double bond makes an aldehyde or a ketone. You put both of those on the same carbon, not somewhere on the molecule, but actually on the same carbon, and you got a carboxylic acid. And then if you trap that between carbons, in other words, you don't have an H here now, you've got carbons on either side of it, you now have an ester. That's chapter 14. And then finally, to finish off the organic chemistry, we have chapter 15 here, amines and amides. And what we're doing here now is we're getting nitrogen. How do I do this? Somehow I'm able to erase that. I forget how I do it.
To the back.
This what? Say,
You just flip it over.
flip.
Is it
That's an eraser. I knew that. Thank you. It's an eraser. It's an electronic eraser. I can't believe it. Okay, that's methylamine. That's methylamine. I told you the best classes are the ones where we help each other out. You wouldn't want me to be here for 20 minutes trying to figure out how to erase that. So who told me how to do that? Rebecca? Stephanie. Okay. Stephanie. Sorry. You're Rebecca. Stephanie. All right. Okay. Hydrocarbons. So this is chapter 10, and the rest of this is chapter 11. All of this is chapter 11. But both 10 and 11, we're going to study hydrocarbons. 2 elements, hydrogen and carbon. Okay, and you're going to see how much variety you can get with just 2 elements, carbon and hydrogen. Chapter 10, saturated hydrocarbons. There's your definition of alkanes. What are alkanes? Saturated hydrocarbons. You like short definitions? That's a short definition. 2 words. Alkenes, alkynes, aromatics are unsaturated hydrocarbons. What do we mean by that? Saturated means the carbons are all surrounded by single bonds. single bonds. Let's just kind of review a little bit from 1305. So from Chemistry 1305, you should remember that Lewis dot structure for carbon. And in a Lewis dot structure, all we put are the valence electrons. And you also learned back there that things like carbon and nitrogen, oxygen, you move on from there, they like to have 8 electrons around them, right? Octet rule. Is this sounding familiar? Okay, it should sound familiar. I don't treat you like, 1305 is history. The 1305 is a prerequisite for this course. So I assume that. So you put a hydrogen there, it donates its electron. And you do that with 4 hydrogens. And then you redraw this like this. And you have this compound, which is methane. That's your first 3x5 card, right? Methane. And it's saturated. The carbons have single bonds around them. And if we went up to ethane, you would put in a carbon-carbon bond, and then you need 3 more things around each one of these carbons. So that's a saturated hydrocarbon. Carbons have all single bonds around. It doesn't matter whether it's a carbon-hydrogen bond or a carbon-carbon bond. They're just all single bonds. Okay, now, remember the movie Honey, I Shrunk the Kids? Long time ago. All right, I'm going to just shrink you folks. Because what we're doing here, everybody's so fascinated with imagination and science fiction movies, using their imagination, imagining things. What are you doing? What are we doing this semester? We are going to, what I'm going to be talking about over and over and over again. I'm going to be talking about things that are generally invisible. We can't see them. We can't see a molecule of methane. It's too small. It is so tiny that it essentially is invisible. Okay? So when we're going to be talking about the molecule at the molecular level and be talking about it like it's something we can hold in our hands, but we can't. But what do? We do all kinds of things to try to relate to this thing that we can't see. I just did a bunch of things. I just wrote a molecular formula. I said, okay, this molecule. Okay, help me out, Rebecca. What do I do now? Stephanie! Look at that. If I get it wrong, it's so hard. That's why I didn't want you to get all confused going ahead onto this chart. If you get something wrong, you have to get it right 4 times. There, that's the molecular formula. Here is a structural formula. All of that's flat. Why? I'm writing on a board. It's 2-dimensional. So all the stuff that we put on our piece of paper and everything is 2-dimensional. The molecule is not 2-dimensional. All right, so I want you to be able to know what you're relating to. What do we do sometimes? Sometimes we say, well, let's try to imagine, let's try to draw this 3-dimensionally. Okay? You can try to do that. But we also have models. This modeling kit, which is made, the black is carbon, and there are 4 holes in that black bead right there at the tetrahedral bond angle, because methane is tetrahedral. 4 faces on this thing. Bottom and 3 sides. It's like a little 3-faced pyramid. Tetrahedral. Where's the carbon? It's right at the center. And so that is a tetrahedral bond angle. You went over to geometry, or over to the math department and into a geometry class, and they drew a tetrahedron having nothing to do with chemistry. And they said, okay, from the center of that tetrahedron out to two of the corners would be a 109.5 degree bond, would be a 109.5 degree angle. Well, that's the bond angle. That's the bond angle. Four identical bond angles, all right? So just keep in mind, we're going to draw a lot of molecule structural formulas. I want you to relate to the fact that they are three-dimensional. So if we went up to ethane, there's ethane. It's three-dimensional. So there's that. There it is. 2 carbons, 6 hydrogens. And one thing, we'll talk a little bit more about this when we get to chapter 11, but there is free rotation around a single bond. This molecule, as it's spinning around and bouncing into things and gets bumped, and these hydrogens want to move, or so they could go like that, which is staggered. The hydrogens on the 1 carbon are staggered, or this one, which is, I don't know what they call it, parallel, all right? So they could line up like this, or they could line up like this, or they could be spinning around in there to some extent. And what affects that? Well, a bunch of things. You heat it up real hot, it's going to probably be spinning. It's going to be energetic. Okay, these are just little pins that we put there so that I don't need to be an octopus and hold all 8 of these things at the same time. Okay? So this is not what you would find in the molecule. What you would find is a nucleus of a carbon, a nucleus of a hydrogen, and electrons being shared between those 2 nuclei. There'd be empty space there. Just like between the sun and the earth, there's no rod that's holding the earth to the sun. There's a gravitational attraction that holds the earth in orbit around the sun. Well, there's an attraction of these 2 elements to one another as they share those electrons. But that is what we would represent as a single bond, 2 electrons being shared, okay? So I'm not going to go into this level of detail all the time, but I want you to be thinking that way. I want you to be making the transition from these 2-dimensional ways in which we're trying to represent this molecule to what it actually is. Okay. Alkanes are organic compounds in which the carbon is bonded to 4 other atoms by single bonds. There are no double bonds or triple bonds. They are saturated hydrocarbons. General formula, CnH2n plus 2. So if there's 1 carbon, so N is 1, 2 times 1 is 2, plus 2 is 4. You got methane. Do I press? So if N is 2, so then 2 times 2 is 4, plus 2 is 6. And that's what that ethane was, C2H6. So that's where we're getting this. 3 times 2 is 6, plus 2 is 8. That's propane. The bond angles in alkanes have a tetrahedral structure with bond angles of 109.5 degrees. There's your, these are the molecular formulas. These are molecular formulas. I asked you to, and I gave you the example of this one, butane, and we wrote out the structural formula, and I encouraged you to make those 10 3x5 cards. I mean, we're going to be using these prefixes over and over again. Meth, eth, prop, bute, pent, hex, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. All right, we'll use them over and over again. On occasion, we'll use these, but up to 6 carbons we'll use all the time. You'll be hearing those all the time. Yeah, so here's 10. 2 times 10 is 20, plus 2 is 22. So that's decane. All right, Lewis dot structure, condensed formula. We're gonna look at structural formula, condensed formula, line formula. As a matter of fact, your first homework assignment, I think, has 12 molecules, and you need to draw all 3 of those structures for those 12 molecules. Structural, condensed, line. So that's what we want to get to here. Some of these slides, like the condensed formula here, really only needs to be this. That's the condensed formula. It doesn't need this line here. I'm sorry that I haven't. Condensed formulas don't normally have the lines. There are some times where they will be there. If there's a double bond, we'll show it with lines, but no lines. There doesn't need to be any lines right there. It's all single bonds. We'll get into that some more, okay? Staggered. We're not going to make a big deal about the conformation. These things can get in different conformations, like that would be staggered, and that would be, I think it's either parallel or aligned or something. All right, but just know that the molecule can get into, it's not changing its structure. When I rotate this around here, the structure is not changing. The only way to change this structure would be to break a bond and restructure it somehow, but no real way to restructure ethane. All right, again, here's propane, and the condensed formula really should just be this. This is the structural formula. It's what I emphasize the most. If you were typing up a paper in Word and didn't want to be doing a lot of drawing, there's a condensed formula. The chemists looked at that, they know that this is that in the condensed version of it. All right, Lewis dot, we'll almost never do this. I just did it a minute ago just to kind of relate to why do you get 4 single bonds around a carbon? It wants 8 electrons shared around it. It wants an octet. So we convert these dots into lines. So a line represents 2 shared electrons. That's a single bond, single bond, single bond. So this is the structural formula. We just mentioned the condensed formula. You're going to love the line formula. That's it. That's the line formula. The line formula, it represents just the carbons. It ignores the hydrogens. And so there's the line diagram for propane. This is all propane. Propane. You're familiar, well, we don't deal with ethane a whole lot, but methane, as I said, that's the natural gas that CPS Energy, there's an entire network of natural gas lines underneath San Antonio, running to all the houses. You use them in your furnace. I was out working in my yard a couple years ago, and a CPS Energy guy was walking the gas line. He had a wand, and what was he doing? he was checking for gas leaks in the natural gas line. This is his job, walking 20, 30 miles a day. That's what he does every day. He walks the line. And I thought, whoa, you get in a lot of walking. But he said, this is very, very sensitive wand. He said, if the line going underneath my driveway had a leak in it, his wand would pick it up. So it's extremely sensitive. So he came up my driveway, and he came right up to the gas meter and checked it and then went on his way. I like to talk to technicians when they're doing things, figure out why they're doing it, how it relates to chemistry. So you know methane. Ethane, I don't know where we come into contact with ethane. Propane, the little white canister out there on your grill out back, propane. Butane, the little lighters. And then you get into heptane, hexane, or pentane, hexane, heptane, octane, you're into gasoline. But what you're realizing there, just as I say that to you, the main thing we do with the alkanes is we burn them. It's the main thing we do with them. We burn them. We use them for energy. Well, let's get another line diagram. Let's just do this one. Let's do butane. Or let's do pentane. So there's the structural formula. Okay, line diagram. Now here's how to do line diagrams. When you put your pen or pencil, use pencil. Even on the homework, use pencil. Because you're learning how to do these things. And you'll do it and you go, oh, that's wrong. You'll erase it and do it right. Okay? When you do this, you put your pencil on the paper. That's carbon number 1, 2, 3, 4, 5. That's pentane. That's the line diagram for pentane. There's our first carbon. And look at the first carbon. The end carbon has to have 3 hydrogens on it. Now, we're not going to draw the hydrogens. We're ignoring the hydrogens. So there's carbon 1, 2, 3, 4, 5. And I emphasize that because what a lot of people do is they go like this. They go 1. That's 2. They're already at 2. They draw the first line, they're already at 2. So they go 1, 2, 3, 4, 5. And how many carbons do they have? 6. They've just drawn hexane, not pentane. So don't make that mistake. Put the pencil down and say 1. Then start drawing. And bend at every 1. In other words, you can't say, oh, that's pentane. No, that's not pentane. That's ethane. That is ethane. I don't care how long the line is. From one end of the line to the other end of the line is the next carbon. Yeah, methane is, there's the line diagram for methane. It's a dot. So forget it. I'm not going to ask you to draw the line diagram for methane.
You're going to be looking for dots.
Yeah, I'm going to be looking for dots. I got a dot right there. Your dot's too small. Okay, all right? So this is how you do it. Bend, boom, 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 and you got it. Oh, wait, before I go on to the next slide. Oh, I'm going to erase this, Stephanie.
Yay.
I'm going to erase that. Let's put in the, all right, so let's put in the condensed formula. So right underneath here, I'm going to put the condensed formula. Just look at that. That's a CH3 group. So I'd write CH. Now the 3 should be down below as a subscript. The next carbon is a CH2. The next one is a CH2. The next one is a CH2. 1, 2, 3, 4, 5. And the last one is a CH3. So there's your structural, your condensed, and your line for pentane. All right? Okay, here's one that's a little bit more complicated. A little bit more complicated. We've got, all right, now we'll get into naming. We're going to get into the IUPAC naming system here in a minute. 5 or 10 minutes we'll be starting to introduce how do you name things. But we'll see. But we got 1, 2, 3, 4, 5 carbons here, and then we have a CH3 group up here. What you're going to see, that's a substituent. It's a substituent off of the main chain. The main chain is 5 carbons long. And then notice right here, we have a Cl. What's Cl? Chlorine. We've got a chlorine attached here. Now I said these are hydrocarbons, and this is about the only exception you're going to see in chapter 10 is that every so often we're going to introduce a halogen. One of these halogens, fluorine, chlorine, bromine, or iodine, they're going to all behave the same way, or they're going to bond, one of them will bond onto a carbon. So in a similar way, they would have different properties, but that's the only thing. So those are what we would call an alkyl halide. Those are halogens. We get a halogen on an organic molecule, we call it a halide. A halide. So this is a halide. So here's our first carbon, CH3. This is a condensed formula. Second carbon, we've got a carbon hydrogen, so CH. But now we got a CH3 there, so we put it in parentheses after this H, CH3. So that carbon has two things attached to it, a hydrogen and a CH3 group. Those are the two things attached to that carbon. Then we get to this next carbon. It has a CH and a Cl. Now I don't need parentheses around this Cl because that's just one atom. But this is 4 atoms. I need parentheses around it. It's a group attached to this carbon. And then we got a CH2 group, and then we got a CH3 group. So there's your condensed formula. And someone is in their mind asking the question, what would the line formula look like? That's a good question. What would the line formula look like? Would you like to know the answer to that? Yes. All right. You're alive. This is interactive. Okay. What are we going to do here? So we've got this. 1, 2, 3, 4, 5. So let's do that line. 1, 2, 3, 4, 5. Okay, now I can't just leave it that way, because if you showed that to a chemist, they say, oh, that's pentane. Oh, no, it's not pentane. It's got that. Well, show me what it's got. What's it got? It's got a CH3 group right there on the second carbon. And on the third carbon, it has a chlorine. We ignore hydrogens, but we don't ignore anything else. We don't even write the carbon. The carbon is all this line is the skeleton of that molecule with a carbon at each one of these bends. Pardon me? Yes, you have to write this. Oh, no, you don't. No, you don't. You're right. Sure. Thank you. You don't need to write that. because there's a line, and what would be at the end of that line? A carbon, and it would have 3 hydrogens on it. So you don't have to write the methyl group. I did that by, I don't know why I did that. All right. Yeah, you don't have to write the methyl group. That's fine right there. But you do have to write this, because if I left that off of there, I would think that's another methyl group. Right? I'd be confused. Don't want to be confused. It could be a chlorine, it could be a bromine. In this case, it's a chlorine. But I mean, you might have a chlorine there, a bromine, a fluorine, an iodine, whatever it is, you got to write it on there, on that line. Okay, this brings us to IUPAC, International Union of Pure and Applied Chemistry. Now, this came about late 1800s, early 1900s, as organic chemistry was, and then what electronics and iPhones are today. They were becoming so, the greatest, newest thing on the market, and newest area of understanding. Everybody was making organic molecules, and now going from Moscow to London to New York to Paris to Berlin, wherever it was, these chemists were working. They were trying to talk to each other about what they were making, and they were confused because everybody was calling molecules different things. So IUPAC said, okay, let's establish a protocol. Let's establish a standard way of naming organic molecules. And let's start applying that so the chemist in England and one in the United States could talk to each other and know that they're talking about the same molecule. Okay, now we have to learn, probably 6 alkyl groups must be learned before we can start applying this. So, and we've already been talking about the methyl. Where does this come from? Well, if this is methane, and it is, if that's a structural formula of methane, so this is methane. We're going to take off the ANE. That is a compound. This thing right here is a group. It will never stand alone. We're going to take off the ANE and add a YL. So when you see YL, you're going to see it a lot. Methyl, ethyl, propyl, hydroxyl. You're going to see a YL. It's going to say, oh, that's a substituent. That's a substituent that's on a molecule. So whenever we see, like in our previous slide, see if I can get back there. 2 previous slides. All right, so there is your methyl. What is here? Oh, it's attached to a carbon. Where is it attached? Second carbon. In this particular case, first, second. It's attached right there. So that's a methyl substituent. So there's methyl. So it's a CH3. Ethyl. Ethyl is a CH3, CH2 with a line. So there's an opening there for it to attach to the chain, or a C2H5 group. So that's the ethyl. So that's 2 of these substituents. Ethane is being changed to ethyl. All right, now the propyl. And this is this is where it starts getting a little bit more complicated. We've got a propyl. Now, we can take a carbon we can take a a hydrogen off of this end right here. And so there would be a place for this to attach. You know, there's a hydrogen here, and a place for this to attach to the molecule. That's a propyl group, or N-propyl group, meaning normal propyl group. Why normal? Oh, it's like methyl, it's like ethyl. We've just taken a hydrogen off of the end. But now, if we take the hydrogen off of the middle, and we couldn't do this with ethane. Ethane doesn't have a middle, just has carbon on either end. But when we got the propyl, we can take a hydrogen off the middle, and we get, so there's a place for it to attach right here. That's an isopropyl substituent. So there's 4 substituents. And I mean, what you can do here now, I told you chapter 1 would have the most 3x5 cards, so don't get too worried. If you want to, you could make a 3x5 card for these. That's the methyl substituent. Ethyl, propyl, and isopropyl. You'd have 2 more 3x5 cards here. Okay, butyl. Butyl, you could have four carbons, because butane has 4 carbons. So when you see butyl, that would be your normal butyl substituent. So methyl, ethyl, normal propyl, normal butyl are just kind of working right down through a series. And then the only other one I really think you have to memorize is this one, tertiary butyl. Tertiary butyl. And we'll cap it off at 6. So what does this thing look like? Kind of looks like this. All right, here's where it would attach. Here's where it would attach to the chain, and you'd have a tertiary butyl group. T-butyl, tert-butyl, or tertiary butyl are all the same thing. Tertiary. So the tert and the T are abbreviations for this word tertiary. All right, so there's 6 substituents to learn. Now we have those. We can start looking back. We can look now at the rules for naming a organic compound. And just let me be clear here. These rules we're going to use these rules not only in chapter 10, but 10, 11, 12, 13, and 14, and 15. All right, so we're laying the foundation for how do you name organic molecules? Whether they're alkanes, alkenes, whatever, how do you name them? So we got methane, ethane, propane, butane, 2-methylpropane. We'll get back to that in a minute. Butane, there's your line diagram. 2-methylpropane, there's your line diagram. I won't dwell on that slide right now. Line structures. We'll talk a little bit later about cycloalkanes. So this is cyclopentane. There's 1, 2, 3, 4, 5 carbons cyclized into they're not in a chain. It's in a ring. And that would be cyclopentane. to be distinguished from pentane. You're going to be introduced to this primary, secondary, tertiary terminology in chapter 12 when we talk about primary, secondary, tertiary alcohols. So I wouldn't worry. It's in chapter 10. You can kind of just skim over that and don't feel like we're totally ignoring it. We're going to talk about it when what's really, really relevant, and that's with alcohols. So don't get bogged down with it right now. Okay, now here's your most important rule. Rule number 1. Find and name the longest chain of carbon atoms in the formula. The longest chain may bend and twist. It is seldom horizontal. Any carbon groups not part of the base chain will be picked up later as substituents. You're looking for the longest continuous chain of carbons. All right, and the substituents will be these alkyl groups. So kind of on rule number 1, just ignore the substituents. Find the longest continuous chain. So I'm going to bring up some examples of molecules, and we're going to apply rule number 1. All right. So for that molecule right there, what is the longest continuous chain of carbons? How many carbons are in the longest chain? 5. 5? How about 7? 7. It says it doesn't have to be. We're not talking about a straight chain. This is not a substituent. Okay, what's a continuous chain? I can put my finger down and I can go through the chain without lifting my finger. 1, 2, 3, 4, 5, 6, 7. All right, it's not 8 because I can't go like this and count that one and come back down in here. This is like a charm bracelet. That's the charm. We want to see how long is the bracelet. Okay? So it's 7. 7. Okay, now what is the prefix that goes with 7? Hept. So what we are now picking up right now is what we call the parent name. Heptane. That is the parent name of this molecule. That's what we get out of rule number 1. That's not the full name of the molecule, but that's the most important part of the name, the parent name. It is a heptane. Right? So that's rule number 1. Here's another one. Okay, find the longest chain here. How many carbons in the longest chain? Well, let's see. If I put my finger down here, there's 1, 2, 3, 4, 5, 6, 7, 8. All right, I can't pick these up because this is a substituent. So this is a substituent and that is a substituent. So it did say identify your substituents. I'm drawing a black circle around them, but you can't see it. Those two are the substituents, but this is 8 carbons long. So what's the prefix that goes with 8? Oct. So the parent name of this is octane. Okay, let's find out what rule number 2 is, because we got to bring in now these substituents. Rule number 2, identify and name the substituents. Okay? So what substituent is this? Methyl. That is a methyl substituent. What substituent is this? How many carbons are in that substituent? So take ethane, and what would be the name? Ethyl. That's an ethyl substituent. So identify and name the substituents. And rule number 3, number the carbon atoms in the chain starting from the end closest to the first substituent. All right? So we want to number the carbons. Let's see here. This methyl group is on the, if this was number 1, 2, 3, we would get to that methyl group. If this were carbon number 1, we would go 1, 2, 3, 4. We'd have to go over 4 carbons to get to this. So this is going to be carbon number 1. It's 8 carbons long. 1, 2, 3, 4, 5, 6, 7, 8. That's going to be the numbering. So I need a pen that will write in white here. Sure. You can do what?
You can change the color.
You can change the
So
color.
just-
Do you have a Surface Pro?
Yeah, I'm using mine right now. Here. So just click the
We're going to have to
little
pay you
arrows.
extra. These are,
Mm-hmm. And then just change it to red, or you can make it any other color.
can I make it white?
Yeah, just here, the circle. Mm-hmm.
Where's white? Right there. Ah. Wait till my wife hears this one. 1. Oh, wait a minute. This is changing my life. 2, 3, 4, 5, 6, 7. See, now the next class is going to just think I always knew this. All right? Yes?
I'm sorry, why do we start from that?
Because this methyl group, why do we start there? Because this methyl group is closer to that end than this ethyl group is to that end.
Okay.
We want to find the end of the molecule that's closest to the first substituent. We don't care what that substituent is. Doesn't matter whether it's a methyl or an ethyl, a propyl, whatever. But which one is closest to one of the ends? And that's going to be carbon number 1. And that then designates the number on every other carbon. It goes 1 through 8. Okay? Okay, now we're piecing this together. There are 6 rules. We're only down to number 3. Oh, and here's that first molecule we did, which is a little simpler one. See, am I still writing in white? I still am. Okay. Let me erase that. Let's go to this simpler molecule. If we start over here, 1, 2, 3, 4, 5, or we start here, it's 1, 2, 3. So this, you don't start on the left and count to the right. It's not what you do. It's the way we read, at least here in this country. It's the way we read, but that's not the way we number carbons in an organic molecule. We find the end that is closest to the substituent. So that's carbon number 1, 2, 3, 4, 5, 6, and 7. All right? Okay, now, how do we still want to piece together the final name. Identify name substituents, number the carbon atoms in the chain. Okay, the methyl is on carbon 3, the ethyl is on carbon 5. So this is carbon number 1, because that gets us to this methyl group quicker. Rules 4, 5, and 6. Designate the location of each substituent by a correct number and name. Assemble the name, listing the groups in alphabetical order. Use di, tri, and tetra if there's more than one of a particular substituent. We don't have that case right here, so we'll come back to that. And ignore those prefixes when alphabetizing. So, let's see what we have here. So what we said here is we've got 7 carbons, so that's heptane. So this is heptane. And it is, the methyl is on carbon number 3, so we're going to put a 3-methyl heptane. 3-methyl heptane. That's the name of that molecule. The 3 is telling us the location of the methyl group. It's on carbon number 3. Heptane is the parent name of the molecule, and then we're naming the substituents. Okay, so this one is 8 carbons long. Yeah, purple might be even better because I can write in black and I can write on the white. So what do we have here? We have octane. So we said the parent name is octane. We have a methyl on carbon number 3 and ethyl on carbon number 5. Now remember that rule number 4 said alphabetize. Alphabetize the groups. So ethyl comes before methyl. So we're going to have out here a 5-ethyl dash 3-methyl octane. Okay? There's a whole lot more we could say about this. But I want to get chapter 10 homework in your hands. And maybe we'll do one of these. Are there 12 sandwiches? I don't know if there's 12. Say 12. If I give you more than 2 here, all right. Did you not get one? All right. Let's see. Eric, could you turn this light on, please? Thank you. All right. Let's pick Well, we've kind of already done methane. Let's see, you got A, B, C, D, that's 5. F, G. Oh, there's only 7. So there's 7 where you need to do the condensed structural line formulas. Let's see. Pick one. Which one do you want to do? What letter?
G.
G? All right, let's do G. G. 2,4,6 trimethyl-octane. Okay. Well, what I would probably do if I were you is I would start with the middle one, the structural formula. So if you're given a name, which you are here, you're given a name of a molecule. Oh, it's 2-methyl. No, it is trimethyl-octane. Octane. So we're doing G. So you're given the name octane, so you know that has how many carbons in it? 8. There's 5, 6, 7, 8. Now I want you to draw your hydrogens. While we're here in chapter 10, just draw everything out. Use pencil so that if you do something wrong, you can erase it and correct it. So there's octane. Oh, wait a minute. No. Sorry. Ugh. Put your octane out there. Okay, put your octane out there. Then it says 2,4,6 trimethyl-octane. Well, you don't have to worry. I mean, we read right to left. Just say this is carbon number 1, 2, 3, 4. Now don't write these on there. I'm just putting them up here. That's 1 through 8. And it says on 2, 4, and 6, what do we have on 2, 4, and 6? We have methyl groups. And it's put the tri in front of it because there are 3 of them. It's telling us there's 3 methyl groups. Where are they? They're right here. They're right here. And they're right here. On the 2nd, the 4th, and the 6th carbons. It says trimethyl, so there should be 3 numbers there. And then fill in your hydrogens. I was getting ahead of myself. I was drawing hydrogens before I got my substituents on there. All right? So the last thing you're going to want to do is fill in the hydrogens. Get your substituents on your structure. So there's the structural formula. Okay, condensed formula. Now it'd be nice to write it right underneath it, but I've got it over here, so let's do it that way. The very first carbon has that. The second carbon has a CH and a CH3 with parentheses around it. Third carbon is a CH2. Fourth carbon is a CH with the methyl group on it. Fifth carbon. Sixth carbon. And I'm running out of room. Seventh carbon is another CH2 group. And then there's a CH3 group. Okay? Now sometimes some people like to try to get creative and see how they can bunch these things together even more with more parentheses, but don't do that. Don't do that right now. Don't get creative. Learn how to just kind of lay it out. Okay, now the line diagram. 1, 2, 3, 4, 5, 6, 7, 8. Isn't that beautiful? Now remember, this is carbon number 1. So that's carbon number 2, 3, 4, 5, 6. And that's the line diagram. Okay, I also had the class project to introduce to you, but I'm not going to try to do it in 30 seconds. Let me just tell you this. It has to do with sugar, the health effects of sugar. Here's the hypothesis. Don't, this will be due next Thursday. All right, this isn't due Tuesday. This will finish next Wednesday. Yeah, today's Wednesday? Yeah, okay. Next Wednesday. So this isn't due Monday. We should finish off enough of this so that you can finish it for next Wednesday. And the class project is going to address this hypothesis. The types of sugars and the amounts of sugar in our average diets is having an adverse effect on our health. Does the available information and studies support this hypothesis? And if so, what are some of the specific conclusions that can be stated regarding either the type of sugar or the amounts and the effects they're having on our health? So it's going to be a class project. Each one of the teams is going to have a particular part of this, but what you can start doing is paying attention to sugar on your food labels, and if you see maltodextrin, go find out if that's a sugar. Okay? Because it might not say sugar, it may say maltodextrin, or it might say sorbitol.
We don't have class on Monday, is it still due Wednesday?
No, we don't have class on Monday. No,
So it's not due next Wednesday?
it's not due next Wednesday. I forgot about that. Monday's Labor Day. So this won't be due Wednesday. I'll get it up on Canvas. So probably due September. What is the next Monday? The 11th. That's probably when it'll be due. We need to go one more lecture, and that'll be next Wednesday, and then you can finish this homework. I forgot. We don't have class on Monday. So see you next Wednesday. See you in a week.